In session 4, we have learned how to create a 1D rod element, how to define material, property and constraints, how to define loads, how to define the analysis type, and how to view the results. In session 5, apart from that, we are going to learn how to create a 1D bar element, define the orientation of 1D bar element, and view the 1D element in 3D. So first, let me show you the problem statement of a bar element subjected to compressive force. Here we are going to use a square cross section. The length and the magnitude of force remains the same, only the direction of force is changing. Material is also changing here. We are going to use different values of Young's modulus and Poisson's ratio. Analytically, we have calculated the stress as well as the displacement. So now, let me show you how to solve this in HyperWorks. First, we will select the user profile as OptiStruct, then click on OK. Now we will follow the same process that we have followed earlier, that is MHPCLL. So first we will create the material, give the name as aluminum, give a color, type as isotropic, card image as mat1, and now click on create/edit. Here we will define the values of E, nu and rho. So the value of E is 7.1 10⁴. Value of nu, which is 0.33. Now click on return. And again click on return. Next we will define a cross section. So go to 1D page, HyperBeam panel. In HyperBeam, go to standard section and select the standard section type as solid rectangle. Now click on create. As per the problem statement, the dimensions of the rectangle is 100 by 100. So here in the bottom left we will define the dimension as 100 by 100. Now if you want to fit this to screen, you can simply click in the graphic area and simply press F from your screen. So F is the shortcut. Now to go back to HyperMesh, click on this icon and now click on return. So HyperBeam is also done. Next step is to define the property. So go to the property icon, make sure you are inside create, give a name to the property, let's say bar, give a color to the property, type as 1D, card image as P bar, material as aluminum, and beam section as rectangle section. Now click on create and return. So property is also done. Next step is component. So go to the component icon, give a name to the component. In our case it is bar. Give a color. Choose the property as bar. Click on create. And then click on return. Now we will create some nodes. So go to geometry page, nodes panel. First we will create a node at 500 00. Next we will create a node at 0, which is at the origin. Now again you can click on the display area and press F from your keyboard, and this will act as fit to screen. Now click on return. Now we will create the 1D bar element. So go to 1D page, bars panel. In bars panel, make sure you're inside the first option, which is bar 2, and here first we will define the property as bar and element type as C bar. Next we will define the orientation. So orientation is how do you want to align the cross section. Take an example here. Let's say you have a water bottle and the length of the bottle is the length of the element. Now if you want to align the cross section, in this case the cross section is the cap, which is a circular cap. So if you want to apply that cap onto that bottle, you have to orient the cap in a particular direction, that is perpendicular to the x-axis in which there is the length. Then only you will be able to apply the cap, or in other words, then only you will be able to apply the cross section. If you orient the cross section in any other way, let's say you orient the cross section perpendicular to the length, then you won't be able to apply the cap. So that is the exact same concept you have to apply in the software as well. You have to orient the elements properly, otherwise the cross section will not be aligned with the element. So here is another example. How it works is, in orientation you have to select an axis. So if you remember HyperBeam, the cross section was created in a particular plane. So if you take a look here, a snippet from HyperBeam, you can see the cross section is created in YZ plane. So what happens is, as soon as you select an axis in HyperMesh, software will align that axis parallelly to the y-axis of HyperBeam. Let me show an example again here. So let's say this is the rectangular cross section in HyperBeam. In the bar panel, I have selected orientation as y-axis. Now what will happen? Software will take the y-axis and it will align that y-axis with HyperBeam's y-axis. So both of the y-axis will be parallel. Now what is the first y-axis that we have selected in bars panel? It is the axis of the global coordinate system. The result will look something like this. You have the blue line as an element. The cross section is aligned perpendicular to the element. On the left side you can see a coordinate system XYZ. This is the coordinate system from HyperMesh. So this is how it will be aligned if you select the axis as Y. Now you cannot select one axis here, and that is the length. You cannot align the cross section on the length itself. You have to align the cross section perpendicular to the length always. So that means out of 3 axes, you can never choose the axis in which the length is present. In this case, x-axis. So we cannot choose x-axis. If you select the element in 3D view, this is how it will look like. Now in a second case, again the same example, but this time I will choose the orientation as z-axis. Now what happens is cross section will be aligned like this, parallel to z-axis of the global coordinate system. So 3D view will look something like this. So if you have a square cross section, it does not matter if you choose y or z, both end result will look the same. But just keep this in mind that you can never select the length as the orientation axis. So now let us go back to our problem. So here our length is in x-axis. So apart from x-axis, I can either choose y or z. So in this case, in orientation, I am going to choose y-axis. You can also choose z-axis and the result will be same. Next, you have to define node A and node B. So for node A, I am going to select the first node, and for node B, I am going to select the second node. And now click on return. Now we have to delete the temporary nodes. So go to geometry page, temp nodes panel, and click on clear all and say return. Now you can also look at this element in 3D view. So if you want to do that, you can go to the toolbar, you can go to this icon, go to the drop down arrow and select 1D detailed element representation. What this will do is this will show you the element in 3D. So you can see how the cross section is applied to the element. If you want to rotate the component, you can press Ctrl from your keyboard and use left click to rotate. So to go back to the 1D view, again go back to the same icon and choose 1D element representation. Now we will go back to XY plane. Now we are going to define the load collectors. So first we will create a load collector. We will give the name as force, give a color, no card image, click on create and return. Now go to analysis page, forces panel, select the node where you want to apply the force, define a magnitude In our case, I want to define a compressive force, so the magnitude is going to be minus 1 lakh. Minus stands for negative direction and the direction is x-axis. And click on create and return. Next, we will define the constraint. So go to load collector icon, give a name as SPC, change the color, make sure it is set to no card image, click on create and return. Now go to analysis page, constraints panel, select the node where you want to apply the constraint, select the degree of freedoms you want to fix, make sure the load type is set to SPC and click on create and return. If you want to zoom in or zoom out of the model, again you can press Ctrl and use the scroll wheel. If you want to move the model, you can use right click using Ctrl. Now the last step is we will define the load step. So go to analysis page, load steps panel, give a name to the analysis, make sure the type of analysis is selected as linear static. Under SPC, select SPC and in front of load, select force and now click on create. Now return. Now all you have to do is save the file and solve the file. So to save the file, go to file, save as model. Here we will give a name to the file and click on save. Now if you want to solve the file, in analysis page, go to OptiStruct panel and click on OptiStruct. Now it will start solving the file. Once the analysis is completed, click on results. First I will go to the XY plane. Now we will go to contour, result type as displacement and click on apply. So this will show us the displacement. In this case the displacement is coming as 0.0704, 7.04 10 to the power minus 2. Next we will take a look at the result of stress. So under result type, choose element stresses. In the drop down, select C bar C-beam axial stresses and click on apply. So here the result is minus 1 10 to the power 1. So that means minus 10. The negative sign indicates a compressive stress. So here we are done with session number 5. So now let me show you the homework. So for homework, you will have to solve similar problem statement for different cross sections. All the inputs are given in this table. So these are the first 5 problem statements. Then you have some different cross sections and the rest of the 5 problem statements for a total of 10. Now once you solve all the 10 problem statements, also make sure that you calculate the stresses and displacements analytically so that you will be able to compare the results. So with this, we have finished session number 5. Thanks a lot for attending session number 5. In session number 6, we are going to cover a 1D beam element subjected to bending force.